Action potential conduction requires both active and passive current flow. The passive electrical properties of a nerve cell axon can be determined by measuring the voltage change resulting from a current pulse passed across the axonal membrane. First, we can use a current-passing electrode to produce a subthreshold change in membrane potential, which spreads passively along the axon. If we then record potential responses at various distances from the site of the current injection, we see that with increasing distance, the amplitude of the potential change is attenuated. If this current pulse is not large enough to generate an action potential, the magnitude of the resulting potential change decays exponentially, with increasing distance from the site of current injection. Typically, the potential falls to a small fraction of its initial value at a distance of no more than a couple of millimeters away from the site of injection. The progressive decrease in the amplitude of the induced potential change occurs because the injected current leaks out across the axonal membrane. Accordingly, less current is available to change the membrane potential farther along the axon. If the experiment is repeated with a depolarizing current pulse large enough to produce an action potential, the result is dramatically different. In this case, an action potential occurs without decrement along the entire length of the axon. Thus, action potentials somehow circumvent the inherent leakiness of neurons. Note that the amplitude of the action potential is constant along the length of the axon. This all or none behavior indicates that more than simple passive flow of current must be involved in action potential propagation. The mechanism of action potential propagation is easy to grasp once one understands how action potentials are generated and how current passively flows along an axon. A depolarizing stimulus, a synaptic potential or a receptor potential in an intact neuron, or an injected current pulse in an experiment locally depolarizes the axon, opening the voltage-gated sodium channels in that region. The opening of sodium channels causes inward movement of sodium, and the resultant depolarization of the membrane potential generates an action potential at that site. Some of the local current generated by the action potential then flows passively down the axon. This passive current flow depolarizes the membrane potential in the adjacent region of the axon, thus opening the sodium channels in the neighboring membrane. The local depolarization triggers an action potential in this region, which then spreads again in a continuing cycle until the end of the axon is reached. The regenerative properties of sodium channel opening allow action potentials to propagate in an all or none fashion by acting as a booster at each point along the axon. Note that as the action potential spreads, the membrane potential repolarizes due to potassium channel opening and sodium channel inactivation, leaving a wake of refractoriness behind the action potential that prevents its backward propagation. The rate of action potential conduction limits the flow of information within the nervous system. It's not surprising, then, that various mechanisms have evolved that optimize the propagation of action potentials. One way of improving passive current flow is to increase the diameter of an axon, which effectively decreases the internal resistance to passive current flow. Another strategy to improve the passive flow of electrical current is to insulate the axonal membrane, reducing the ability of current to leak out of the axon and thus increasing the distance along the axon that a given local current can flow passively. Among vertebrates, this strategy is evident in the myelination of axons, a process by which glial cells wrap the axon in myelin, which consists of multiple layers of closely opposed membranes. By acting as an electrical insulator, myelin greatly speeds up action potential conduction. The major reason underlying this marked increase in speed is that the time-consuming process of action potential generation occurs only at specific points along the axon, called nodes of neuro5e, where there's a gap in the myelin wrapping. An action potential generated at one node of neuro5e elicits current that flows passively within the myelinated segment until the next node is reached. This local current flow then generates an action potential in the neighboring segment, and the cycle is repeated along the length of the axon. Because current flows across the neuronal membrane only at the nodes, this type of propagation is called saltatory, meaning that the action potential jumps from node to node. The result is a greatly enhanced velocity of action potential conduction. For example, whereas unmyelinated axon conduction velocities range from about 0.5 to 10 meters per second, myelinated axons can conduct at velocities of up to 150 meters per second.